Okay, I hope it's working. Hello, guys. So I decided to not overcomplicate things, and I don't have a lesson as I promised last time. So whenever I don't have a lesson, I am here on YouTube making a lesson for everyone. It's live, but again, I made it private just in case I mess up. So for now, I am not used to YouTube just yet. So let's just continue. So last time we did reactivity 1-1 for IB DP chemistry. Today I was thinking to make to explain reactivity 1-2, but I don't know how much we will cover because I'm not preparing. Yeah, so I'm trying to make it simple for me. So we just start with reactivity 1-2, that's SL, yeah, and hopefully we will cover bond enthalpy and maybe Hess's cycles. We'll see how fast I'm going. Okay, so we start with reactivity 1-1, that's bond enthalpy SL, yeah. Obviously, if you're HL, you also need this. So definitions. I normally don't pay much attention to definitions because I say, okay, you just have to memorize it before the exam. But for this one, I would like to pay attention. So average bond enthalpy, it's the energy needed to break 1 mole of covalent bonds in a gaseous molecule to form gaseous atoms averaged over a range of similar compounds. And there is so many things that can go wrong with this definition. Yeah, so for some reason, they're really strict in A levels and in IB and even in GCSE with this kind of definition. So for IB, you need average bond enthalpy. Yeah, so the gaseous part, it's like 1 mark. Yeah, so you have to say that it's energy needed. So first of all, energy needed. Yeah, so that's like endothermic process. So you need to supply energy to break a bond. So energy needed to break 1 mole. 1 mole is essential of covalent molecules in gaseous state, yeah, or in gaseous molecules. So you can only apply bond energy, strictly speaking, to gaseous molecules, and sometimes they would ask you to apply it to like liquids or solids, and then they would ask what was wrong with your answer, and usually what's wrong is that you used not gaseous substances but liquids or solids. Yeah, so you have to remember that strictly speaking, bond energies are applied to gaseous states only. And since it's averaged over a range of similar compounds, right? So for example, if it's a CH bond, it could have been averaged over like methane, ethane, propane, and so on. Yeah. So these are not the precise values as we would see is the case with enthalpy change of formation and combustion. So these values are averaged. And actually, this is not the best example because, well, I'll explain on this one and then say why it's not the best example. So if you're talking about bond enthalpy for hydrogen, what does it mean? So we're breaking 1 mole of covalent bonds in gaseous state. Yes, you have to have one in front of H2. So you're breaking 1 mole of bonds to form like whatever. Here you'd form 2 moles of hydrogen gas atoms. Yeah, so G is important, one in front of H2. You don't have to write it, but you have to remember that bond energy, it's per 1 mole of bonds broken, not per 1 mole of atoms formed. Yeah, if it's per 1 moles of atoms formed, so if you put 0.5 H2 gas goes into H gas, that's not bond, that's half of the bond enthalpy. That's another type of enthalpy which we would cover for HL. Right, so now why is this not a good example? Well, because hydrogen mole, and actually there was a question like this. So hydrogen bond is only present in hydrogen molecule. Yes, so HH bond is only present in hydrogen molecule, so you cannot really average it over a range of different compounds. Yeah, so this is not an averaged value because it only exists in hydrogen. And remember that bond making, it's an exothermic process, so when bonds are formed, energy is released. It may be, well, for some people told me it's counterintuitive, but then just memorize it if it's counterintuitive to you. So bond forming, it's exothermic. Yeah, so energy is released when a bond is formed, and bond breaking is endothermic. So when bond is broken, you need to supply energy. And enthalpy change for a reaction can be calculated as energy of bonds broken, which is energy of bonds of all the reactants. Yeah, because in the reaction we're breaking bonds of reactants, minus energy of bonds formed, that's bonds of the products. And bond enthalpies or bond energies, they're given in the data booklet. So let's see, example. Calculate delta H of reaction of the following reaction, and these are bond enthalpies from the data booklet, from some data booklet I've taken. So whenever you have a question, because we would also study, especially for HL, we would study other ways to calculate enthalpy change, and they would tell you that you need to use a table, some number of the table. I forgot what it is for bond energies for the new data booklet. But in any case, they would tell you which table to use. Yeah, so be careful because for bond enthalpy, it would be one table. For enthalpy change of combustion and formation, it would be another table. So, okay, so here I'm telling you, yeah, so the question is calculate delta H using bond energies. And these are the values from the data booklet. So to solve this question, what we need to do is I recommend to rewrite the equation in such a way that you see all the bonds. Yeah, so don't just go with molecular formulas, but draw it structural. So I'll just redraw it. CH4. I will write without state symbols. Everything is gas. It doesn't matter for us. Then 2O2, oxygen in O2, it has a double bond. If you don't know it, then you have to draw the U structure and calculate it. Yeah, of course, usually for these questions, there wouldn't be anything difficult. So usually it would be like O2, Cl2, CO2, so some very straightforward molecules. But if unsure, just draw a U structure and see. Yeah, you have to know how to do it from U structure. That's in bonding topic. CO2 again, it's oxygen double bond C double bond O. If you don't know it, you have to draw the U structure and calculate whether there are single or double bonds. And water with hydrogen, you can only have single bonds. Right. Then usually these questions are 3 marks. Yeah, so don't make it in one go. So don't make it in one go as bonds broken minus bonds formed. Calculate bonds broken first, then bonds formed, and then delta H of reaction. Because if you make a mistake, you can have this ECF error carried forward. Hopefully, it would still stay in the mark scheme. And then if you make one mistake, you lose just 1 mark if you make it in steps. But if you make it in one go, you lose all marks if your final answer is wrong. So calculate it like this. So bonds broken. So which bonds are we breaking? Well, let's mark them. Yeah, so we're breaking all the bonds of reactant. So I'm breaking 1, 2, 3, 4 CH bonds. And I'm breaking in reactants 2 bonds of oxygen, oxygen double, oxygen, oxygen double bond, and then plug in the numbers. So CH 4 times 413 plus plus 2 oxygen, oxygen double bond 498. Also be careful, oxygen oxygen double bond is not the same as 2 oxygen oxygen single bonds. Yeah, so when you're looking at the data booklet, choose the correct number of bonds, yeah, in between the atoms. Okay, and then we calculate. Where's my calculator? So 4 times 413 plus 2 times 498, that's 2648 kilojoules. Then next, bonds formed. So which bonds are we forming? So all the bonds of reactants are formed. So we're forming 1, 2 CO bond, C double bond O. So that's, no, that's not all yet. So that and plus we're forming, okay, so now what else are we forming? We're forming 4 OH bonds. Yeah, so careful here. So you see 4 OH. Why is it 4? Because we form 2 water molecules, 2 H2Os, and each water molecule contains 2 OH bonds, right? So you see this is one water molecule. It has 1, 2, 2 OH bonds, and have 2 molecules like that. So basically it's like this is the first molecule, this is the second molecule. So how many OH bonds in total? I know you cannot see it. Yeah, it's 1, 2, 3, 4 bonds. Okay, so not 2 but 4. So plus 4, 4 OH bonds single. And then the number is plugging in. So 2 times CO 805 plus 4 times OH 464. 4 times 464, that's 3466 kJ, kilojoules. And then subtract. Yeah, and then we use the formula that delta H of the reaction equals to energy of bonds broken minus energy of bonds formed. So that's 2648 minus 3466. 48 minus 3466, that is negative 818. And so whatever sign you get, that's the correct sign for this reaction. If it's negative, it's exothermic, positive endo. Okay, done. First question done. One more. Let's say this question, we have a reaction, calculate the enthalpy change for the forward reaction shown in the equation. Using Bond enthalpies. Yes, this is also from some data booklet. So again, I will rewrite this equation so that I see all the bonds. You need to know that nitrogen is triple bonded. If you don't know it, again, you have to learn how to draw U structure and then you'll know. Hydrogen, it's obviously single bond and 2NH3. Here, even though there are lone pairs. Yeah, for example, there are lone pairs on nitrogen. I don't have to draw them because lone pairs don't do anything. But if you draw a proper U structure, you would also see that there are lone pairs, which we don't need for this. Yeah, but still you need to know how to do it for the exam. Okay, and calculating separately again. So energy of broken bonds. What are we breaking? We're breaking triple bond in nitrogen, 1. Triple bond, and here you see they give us the choice, like which nitrogen we're choosing. Well, we'll choose this one. Yeah, nitrogen, and we're breaking 3 HH single bonds. These, so and it's a good idea to mark them because normally like you can just miss some of the bonds. Yeah, so better to mark. Okay, so nitrogen triple bond is 945 plus 3 times HH single, 436. 945 plus 3 times 436 is 2253 kJ, and then bonds formed. So we're forming the bonds of the products. Forgot which color I used. Okay, let's do this one. Okay, now again, careful. Yeah, so we're forming 2 NH3 molecules. Each molecule has 1, 2, 3 NH bonds. Okay, so it 3 times 2, so it's 6 NH bonds in total. Okay, so if it's difficult, you can just, instead of 2NH3, you can really like write like 2 NH3 molecules, like NHHH, that's the first molecule, and the second molecule right next to it. Yeah, and then calculate how many bonds do you have in total. So 1, 2, 3, 4, 5, 6. Yeah, of course you have to do it fast. Yeah, but like if you're just starting, you can do it like this and just write down all the molecules. Okay, so 6NH. That's 6 times NH, 391, which is 2346 kilojoules, and then we subtract. Yeah, so we remember we don't do it in one go. We do bonds broken first, then bonds formed, and then we subtract, just in case you make a mistake, so that you don't lose all 3 marks. 2253 minus 2346, so negative 93 kilojoules. That's it. So these questions are, I think, one of the easiest in the syllabus in both A level and IB, but you have to be sure that you've written the formulas correctly. Yeah, so you have to be sure that you haven't like confused double bond, single, triple bond, and then it's easy. And 3 marks, I think that's quite a lot of marks for such an easy question. Right, next. I think I don't know how much time I've already spent. It doesn't say. 14 minutes. Okay, so I think we can do one more. Maybe 14, maybe not. Approximately. We can do one more bit of the topic. So that's Hess's law. It's also SL part. So it would be 1, 2, 2. So the definition, you don't really need the definition, but it is in the specification, so I'll tell you. So Hess's law says that the enthalpy change accompanying a chemical change is independent of the route by which the chemical change occurs. A lot of chemical word here, but I'll explain what does it mean. So let's say you have a reaction, CH4 plus O2 goes into CO2 and 2H2O. I hope it's balanced. Yeah, it is balanced. Well, the enthalpy change of this reaction, so if we draw it on the enthalpy level diagram, yeah, so it's exothermic because it's combustion, so you would have reactants here and products, the final products there. Yeah, so these are your reactants, these are your products, CO2 and 2H2O. So the enthalpy change of this reaction, let's say it's like negative 890, whatever number it is. So the distance in enthalpy level diagram from reactants to products, it's minus 890. Yeah, so like, well, plus 890 going down because it's exothermic. But now if you could make this reaction through some intermediates, yeah, so for this particular reaction, it's maybe not that easy to do, but if you could make this reaction and first turn CH4 and O2 into something else, not into CO2 and H2O, but for example, into CO and water, and then CO and water reacting with O2 would go into CO2, right? So these are intermediate. So it's something that is formed before the real product is formed, right? So you have your reactants, they form into something, and then that something, which is intermediate, forms the product. So if we could do this reaction like this, then Hess's law tells us that enthalpy change of this reaction where reactants are going into intermediates, let's say it's delta H1, it would first make a reaction with delta H1, and then these intermediates would turn into final products with enthalpy change delta H2. And so Hess's law tells us that delta H of the reaction would equal to delta H1 plus delta H2. Yeah, so it doesn't really matter whether CH4 and O2 directly turned into CO2 and H2O, or whether it first turned into some intermediates and then those intermediates turned into final product. So Hess's law says that this final enthalpy change of reaction would equal to the sum of all the intermediate reactions. And if you add them up, let's see if that would hold true. So reaction is minus 890, and that equals to this reaction, so minus 607, plus this reaction, minus 283, and it should be the same. My mental math is very slow today. Yeah, that works. Mm-hmm. Yeah, so that's Hess's law. Yeah, so first you can turn your reactants to intermediates, then intermediates change into products, and you can have as many steps as you'd like. As long as reactants and products are like a set species, then enthalpy change would not change. Yeah, so it would stay as 890, for example, in this case. This is like a theory. Yeah, so you would need this for HL when we do Born-Haber cycles. For SL, I'll just show you how to do it quickly without any cycles and without too much thinking, honestly. So let's try this question. So consider the following reaction. So you're given two reactions. Enthalpy change for the first reaction is that, for the second reaction is that, and they ask you to find enthalpy change for some other reaction, for some third reaction. So how do we solve this? So what we do is we look at the reaction for which you need to find the enthalpy change. So you need to find enthalpy change for this reaction. Look at the first substance. So your first substance is Fe2O3. Okay. You want Fe2O3 to be with the coefficient of 1 on the left side of the equation. You want it to be with the coefficient of 1 because it's 1 here, on the left side of the equation because it's on the left side. Now we find Fe2O3 in the equations for which they give us enthalpy changes. Yeah, so it is here. Okay, found it. Let's see what do we need to do with it. So it's with the correct coefficient. Yeah, it's with the coefficient of 1. So that's good. That's how we want it to be. But it's on the wrong side. We want it to be on the left side. So it means that we need to flip this equation. Okay, I'll flip it. Let's say this is equation 1, this is equation 2. So equation 1 I'm flipping goes into 2f. I will not write state symbols just to save time. I flipped it, and when I flip the equation, enthalpy change would change the sign. Yes, so it used to be x, now it's minus x. So now I figured out what I need to do with the first equation. Now I have to figure out what I need to do with the second equation. So let's look at the second substance. Second substance is CO. So we want it to be on the left side with the coefficient of 3. Let's find CO in our equation here. So there it is. The CO now, it's on the correct side, on the left, that's how we want it to be, but the coefficient is 1, not 3, how we want it. That's why the second equation I would need to multiply by 3 without flipping. And no flipping because it's CO is on the left side already. Yeah, it's the side is correct. Okay, so I multiply every single coefficient by 3. O2 goes to 3CO2. And once I've done that, I also multiply enthalpy by 3, so 3y. And essentially that's enough. I will also add them up now just to show that if you add up the first equation and the second equation, you'd get the equation that you need. But of course, usually like once you've solved maybe 3 or 5 questions like that, you don't have to do it. You would see the answer right away. So now I will do this. So once I've done the manipulations with my two equations, so I know what I do with every single one of them, I will add them up just to check. And once I've added them up, I will get the equation which I need, for which I need to find the enthalpy. If you get something else, it just means that you've done something wrong, yeah? But okay, let's do it. So I will add the first equation to the second equation. And how do I do it? So you add left parts of the equation, and that would equal to the sum of the right parts. Yeah, so basically this is my left part of the first equation, and I'm adding it to the left part of the second equation. So that's what I do. Fe2O3 plus 3CO plus 3 over 2O2. That's my left parts, and that equals to the sum of the right parts. So this is the right part of the first equation, that's the second, so I'm adding these. So 2Fe plus 1.5 O2 plus 3CO2. And then we can cancel out identical species. So 3 over 2 O2, it's like 1.5 O2 and 1.5 O2 cancel out. So you can cancel out molecules that are, or like species that are the same on both sides with the same coefficients. Yeah, so oxygen cancels out. And eventually what you get is this 2Fe plus 3CO2. So that's exactly what we wanted to get. Yeah, so we wanted Fe2O3 plus 3CO goes into 3CO2 and 2Fe. And since I've added equation 1 and 2, my enthalpy changes would also add. So it's minus x plus 3y. So that's the answer. So it's A. But again, this final part, you don't really have to do it. Yeah, so you can do it a few times just to see, just to practice and to, prove it to yourself that it works. But then in the exam, I think you just see Fe2O3, you flip it because it's on the wrong side, and then you see CO, you multiply it by 3 and add, and that's it. Let's do one more example. Two reactions of iron are shown. What's the enthalpy change? Okay. First substance, FeO. Where is it? It's here. I want it to be on the left side with the coefficient of 2. Now I have it on the right with the coefficient of 1. What do? I flip this equation, so I change the sign, and multiply it by 2. Yeah, that's how I do it in the exam. My camera is blocking everything. Yeah, so I figured out that I have to flip, so change the sign, and multiply by 2 because I want to have coefficient of 2 in front of FeO. Now, next substance. Next substance is oxygen. And here, be very, very careful. You cannot do anything based on oxygen because you see you have oxygen on both sides. Yeah, so the substance that you're choosing to use, to figure out what you do with the first and second equation, it has to be unique, right? So if I had iron here somewhere, I wouldn't be able to tell because you see iron is also in both equations. So oxygen, I don't know what to do with it. Yeah, I just skip it for now. So oxygen is in both equations, so I'm skipping oxygen. And then the next substance is Fe2O3. It's here and it's unique. Yeah, so using Fe2O3, I know what I do with the second equation. Actually, I do nothing because Fe2O3, I want it to be on the right side, and it is on the right side. And I want it to be with the coefficient of 1, and it is with the coefficient of 1, so I don't change it. So just minus 822. And that's it, and then you just add. Again, you can do it, you can flip the first equation, multiply by 2, and add to the second one, and check if everything is right, if you get this equation or not. But in the exam, I would just do it like this. So I just calculate times 2 plus negative 822, and that looks like maybe B or something. Let's check. Times 2 minus 822. You can use calculator now, so it's all good. Yes, 8kj. So B. Okay, one more. Again, you have two equations. What's the enthalpy change in kJ per mole for the following reaction? All right, so first I have CH4. It's here and it's unique. What do I need to do? So I just need to flip it because I want it to be on the left side. And in this first equation, it's on the right side. So I'm flipping. Coefficient is correct. Then carbon is not carbon is there, yeah, but I already used the first equation, so it's already flipped. Then hydrogen, let's look at hydrogen. Hydrogen, because I need to know what I do with the second equation. Yeah, the first equation, we already decided what we do based on CH4. That's why carbon doesn't give me any new information. It's in the same equation as CH4. But hydrogen does give me new information. I want it to be on the right side with the coefficient of 4. Here, it's on the right side, but the coefficient is 2, so I need to multiply this by 2. Yeah, and also careful, of course, you have to be very careful with the indices and so on. So this hydrogen is not the same as this. I hope you see it. Yeah, this is H2 here and here, and this is H atoms. Yeah, so just careful um, with the indices. So we decided that the first equation we're flipping, the second equation we're just multiplying by 2. So your answer would be, and then you add 436 times 2 should be D, I think. Yeah, 75 plus 436 times 2. Yeah, 947. That's D. Right, okay. Um, yes, well, that's how you do Hess's cycle in practice in the exam. Yeah. If it's multiple choice, so you do just like that. If it's open response, I would maybe rewrite equations and add just in case, yeah. But usually if you get the correct final answer, you get full marks. Right, and the final bit that we will cover is that, because already almost half an hour. Okay, yeah, so the final bit that we'll cover is Hess's cycles that are written as triangles. Yeah, this is something that you don't really need for the exam. I mean, they might give you something and then like pre-filled Hess's cycle, which you have to fill in, but some teachers, they really um, like giving these tasks, so you might need it for your predicted grade. Let's see what you do with the cycles. So let's say you have this is just basically the Hesse cycle, the same as I showed in the beginning, yeah, but just written in a different way, in the triangle way. And usually in these cycles, at the top, you write a reaction for which you need to find enthalpy change. So let's say we need to find enthalpy change of this reaction. And at the bottom, you write some kinds of intermediates, yeah? So in this case, it's like sodium, solid, H2 gas, C, graphite, O2 gas. And they would give you enthalpy changes for some reaction. So let's say you know enthalpy change of this reaction. Let's say it would be delta H1. And you know enthalpy change of this reaction, delta H2. Right? Again, normally they don't ask you to draw the cycle from scratch. I haven't seen questions like that, but they can give you a pre-filled, like half-filled cycle, yeah, or even completely drawn cycle, and you just have to figure out how to find enthalpy from that cycle. That's why I won't be teaching you how to draw it. For A level, you do need it, but for IB, like most likely not. Maybe you lose 1 mark if they ask to do it, yeah. But you need to know how to find delta H of reaction if you know delta H1 and delta H2. So let's see how you do it. Especially if you're HL, pay attention to that because we need it for Born-Haber cycles later. All right, so let's say we need to find enthalpy change of this reaction. So this is my direct route. So you want to start at NaHCO3 and you want to end with this Na2CO3 or whatever. So this is direct route. So you can do it directly with enthalpy change delta HR. So I say delta HR equals to, And then you can do it indirectly through intermediates. So you can first do this reaction. Yeah, why do you do this reaction first? Well, because this is your start. So you want to start here and end here. So if you start here, you can do this reaction first, and then you do this reaction, right? And you would end where your end is. And when you do this reaction, you're doing a reaction that's opposite to delta H2, right? Because delta H2 goes opposite direction. So when you're opposing the arrows, you're opposing the arrow, you're changing the sign. So it's minus delta H2, and then you're doing this forward reaction, which follows the arrow, how it's printed. Yes, so for a reaction that they give you. So it's plus delta H1. So if these were numbers, that's how you would calculate it. Okay, one more example. Let's say you need to find enthalpy change of this reaction, and let's say it's delta HR. That's what you need to find. Yeah, that's what we need to find. And you know enthalpy change for this reaction. Let's say that's delta H1, and this is delta H2. So this is your direct route. So you say delta HR equals 2. So this is your start, this is your end. Yes, so you go from start to end. That's direct route. And then if you go indirectly from start to end, you'd have to do this reaction first and then this reaction, right? So you first do this and then this reaction. So you'd start again here and end here. And that's why this reaction follows the arrow, right? So you're doing the exact reaction which they gave you. So it's delta H1, so you're not opposing the arrow. Here you're opposing the arrow, so minus delta H2 because you're making a reaction that's opposite to the one that's printed. So that's how you find delta HR. And last example, let's do this one. So let's say you need to find this. So delta HR, and this would be delta H1, delta H2, delta H3. Yeah, so you know delta H1, delta H2, delta H3 from the, I'll write it R like this, from the data booklet, or like they give this in the question. So this is your direct route. That's what we need to find. Yeah, so we say delta HR equals 2. And now so this is your start, this is your end of the cycle. Now indirectly, what do we do? So we need to convert carbon to CO2. So we need to do this reaction first, then we need to convert hydrogen to water. We do this reaction first, and then we do this reaction. I need to use another color. Wait a second, to show that it's indirect. Yeah, so the pink one is direct route, and this would be indirect, the yellow. Okay, yeah, so you converted these guys first into CO2 and water, and then CO2 and water to whatever, like C2H6. And that's why, so it's H1, you're following the arrow, so just H1 plus H2, delta H2, you're following delta H2 arrow, and then this arrow you're opposing because delta H3, it's the reverse reaction to the one that you're doing. Yeah, so you see the yellow arrow is opposing, that's why it's minus delta H3. Yeah, so the yellow arrow that I need to do, it's opposing the one that's printed, the one for the reaction that they've given. And if these are numbers, just plug in the numbers. Okay, that's it. I think that's enough. So next time, hopefully we can do HL for combustion formation enthalpies. Right, I will stop the stream, but it may cut off. I don't know when it cuts off. I think I'm cutting off the end of the stream all the time. So, okay, let's see. See you next time.